This video looks at implementing the mechanistic lag compensation design using MATLAB tools. So the previous video introduced the links between the key attributes of a lag compensator and the margins, and from these showed how you could come up with a mechanistic design approach for lag compensation, which would give you a design that was probably quite close to the best that you could do. Now this video will show how you can use MATLAB tools in order to implement this design, and the key thing is very quickly and efficiently. So let's remind yourself what these mechanistic rules were. First, specify the desired phase margin, and remember this particular part of the design is arbitrary, but it's likely you're going to want something 50 to 70 degrees for most systems where you could use a lag compensator. Next, find the frequency omega, which gives you this phase margin minus 180, and choose the gain k so that this becomes the gain crossover frequency. And you remember these three steps are in fact the simple gain design. Next, choose the required gain recover at low frequency, and that's going to be a factor beta, and your compensator is given by this formula here, k s plus omega over 10 s plus omega over 10 beta. And you've got a reminder in this box down here, this design rule relies on the arbitrary decision of a desired phase margin. Right, now many books will argue that you should in fact add 5 to 10 degrees to the desired phase margin in steps 1 to 3, because the phase margin from the lag is 5 to 10 degrees worse than that for the simple gain design. Okay. Now personally I think that given the initial choice of phase margin, so I'll put it here, the initial choice of phase margin is somewhat arbitrary, actually adding another 5 to 10 degrees is also a little bit arbitrary and may or may not have a significant impact. So I think you have to look at the holistic problem and decide what's best for yourself. However, always follow the lecturer's instructions. So if the lecturer insists that you add this 5 to 10 degrees, then do it. Right, using Caesar tool, this video will give a number of worked examples showing the mechanistic design approach and how this compares to the simple gain design. And the key contribution of this video is to demonstrate how you can use MATLAB tools. In all cases we're going to use a phase margin or a starting phase margin of 60 degrees, and we'll use beta equals 5 for convenience. In many real systems it will actually specify what beta you need, and there will be a reason behind that. First example then, g of s equals 0.01 over s plus 0.2, s plus 0.1, s squared plus 0.4s plus 0.2. So we'll go straight to MATLAB, enter that, and move on. So we've already entered it into Caesar tool, so I'm just getting the Caesar tool windows open. There they are. So you can see for this particular system, with a compensator of 1, you can see the margins are currently very large. So first step, we want a 60 degree phase margin. So with this MATLAB tool I can pick up this gain plot. You can see as I move the cursor over it turns into a hand, and I'm going to drag this bode diagram up until I get about a 60 degree phase margin. They are 61.5, is not too far away, that's good enough. And if I look over here, you'll see that the gain that I've used is 9.2. So what I might do is if I change that to 9.1 just to keep the numbers a bit simpler, check what that does. That gives me 62 degrees, maybe 9.2. Okay, 9.2 will do. Okay, you could be more precise if you wanted, but remember decimal places really make little difference. Now, what's the current gain crossover frequency? I read that down here and it's 0.164. So what I need to do now is, if I write on the screen, remind you of what my compensator will be. It's going to be 9.2 into s plus 0.0164 over s plus 0.0, and then I was going to divide by 5, so I get 0.033. that's close enough. Okay, so you'll see I've used my formula s plus omega over 10 over s plus omega over 10 beta. So now I need to enter that compensator over here. So I'll go into this particular bit and I'm in compensator editor and I want to add a lag. Now you'll see it defaults to give me s plus 10, s plus 1, which is not what I want, so I can go here. I might make this window a bit bigger in order to change those. So where do I want the real 0 to be? I want it to be minus 0.0164. And where do I want the real pole to be? Again, minus 0.0033. And what I'm going to do is I'll make that 5 just for the pedants who want the beta to be exactly 5. And you'll notice sometimes CISO tool goes and changes your gain, so I need to go and put that back 9.2. And the most important thing for you to do at this point is to look at the formula CISO tool's got here and make sure it's the same as the formula you wanted, which you had here. So in these two cases you can see I've got the same formula, so hopefully I've got this right. So let's just make that box a bit smaller again. And now let's have a look and see what's happened to our margins. Well, you'll see the new phase margin is 56.3, which, as we said, is about 5 degrees below what we had with the simple gain design. So I'm now confident that I'm on the right ballpark. So now I'm going to get rid of these because otherwise they will get in our way later. So the next question you might ask is, well, has this lag compensator been any good or not? Well, here's the closed loop responses. You can see there's the output, there's the input. Difficult to tell with CISO tool sometimes, in fact, whether the design is effective. So what you've got to do now is you've got to go back to the MATLAB window. Alright, and I've entered some code here so we can actually do a comparison. You can see of the simple gain design K1 and our lag compensator. So first thing I've got to do is export my lag compensator. So let's go here and export it so that we have got it. So I'll go export compensator, and what I'm going to do is call it K1 lag. So export that to the workspace, and then K1 I knew was 9.2, so I'll just write that one straight in. K1 equals 9.2. There it is. And now I can look at all the boat diagrams together. So there it is. There's all three boat diagrams. Okay, I've got the before, which was the blue, and I've got the simple gain design, which is the green, and I've got the lag compensator, which is the red. And you'll see that the red has got this gain recovery at low frequency as expected, but also got this characteristic phase dip, but the phase crossover frequency is over here, so it doesn't matter too much. Now what I can also do is I can look at the closed loop step responses with and without this lag compensator. Now hopefully that's... oh, it wasn't happy about something. Let's just check what it wasn't happy about. I remember. That was very careless of me. I forgot to update my folder. That's why I wasn't happy. Right, now it'll go again. Right, so there's the step responses with the simple gain design and with the lag compensator. And what do you notice the key difference is? Simple gain design goes to about 0.7, quite a large offset. With the lag compensator, you can see it's going up here, it's a much higher value, a much smaller offset. So the lag compensator has delivered what I expected. It's giving me a smaller offset. And in fact, if I look at the input responses, there's not a lot of difference as expected. However, I might also want to look at the disturbances, so let's just look at what happens if I have an output disturbance. That's that one there. And so where's that gone to? Probably this plot here. And you'll see if I have an output disturbance, again, do you notice that with the lag compensator I get a much smaller offset? See, this green line has gone a lot lower, so I've managed to reject the disturbance better with the lag compensator than without. And I can also look at input disturbances. and you'll see a similar impact. When you have an input disturbance with a lag compensator, you see it's rejected the disturbance much better than with just a simple gain design. So hopefully the benefits are obvious, and you can see using MATLAB tools it's very easy to see what's going on. Right, next I'm going to look at system G2. So let's go back to here and let's clear all our designs, all compensators, and let's import our system G2. Okay, so there's what we've got for G2. Now I better bring up the other two windows just so we can see what's going on. Alright, now our first step, we said get ourselves a 60-degree phase margin. The current phase margin's 18. So what I'm going to do is pull this down a bit, pull the gain plot down until I get about 60 degrees. There we go, that's close enough. So you can see the gain I've used, if you look at it over here, is about 0.065. Okay, now what's the gain crossover frequency? It's 1.13. So perhaps if I write again, just so that we don't lose it, the compensator that we want, so we want K equals 0.065 S plus 0.11 over S plus 0.2. Okay, in fact perhaps for simplicity I'll just put S plus 0.1 over S plus 0.02, isn't it? Get it right. You'll notice I'm not being too pedantic about decimal places because it often doesn't make that big a difference. Okay, so let's add our lag. And again you see we can change the pole and zero location, so we said we wanted the 0 to be at minus 0.1, wanted the pole to be minus 0.02. Go and replace what our gain was. It was 0.065, or close enough. There we go. And what do you notice after we've put the lag compensator in? You can see we've got 56 degree phase margin, so about 5 degrees worth in the 60 we started from, which is roughly what we expected. And you can see this classic phase dip which you get from the lag, but it's to the left, so it doesn't worry you too much. And there you can see the closed loop response. Now here it's worth noting, can you see this very slow mode that comes from this lag compensator? If you had a simple gain design you wouldn't have this very slow mode gradually settling, and we'll look at that again when we go back to the MATLAB window. But first what I've got to do is export this compensator so we can do our comparison. So we're going to now call it K2 lag, because this is the second system. So if I export that to the workspace, then hopefully we've got K2 lag, and K2 was 0.065, so I'll enter that one directly. So K2 equals 0.065, and now if I go to my window here, my text editor window, then I can look at the bode plot of all three of these together. Perhaps what I'll do is I'll put the legend so we can see. So where's the bode diagrams gone? There we go. So you can see the bode diagrams here. Before K equals 1, and then simple gain design in the green, and with the lag compensator in the red. And you notice the same message as before. The red line is above the green line at low frequencies in the gain plot, so you've got gain recovery. And in the phase plot you see this classic phase dip from the lag compensator, but the gain crossover frequency is over here, so that phase dip doesn't matter too much. Alright, if we look at the step responses for the closed loop, that's with the simple gain design and with the lag compensator. What do you notice? In this case, the lag compensator, which is the green, looks worse. Can you see the green plot here? It's got a bigger overshoot and it's got this really slow mode, slow to settle. And in this case you might be saying, why am I bothering with a lag compensator? It's actually worse than the simple gain design because it's introduced this slow mode. And you'll notice here the system already had an integrator, so you might say, well, I didn't need gain recovery because I've already got an integrator. And so if I put in gain recovery, it's just made my margins worse and made my performance worse. So let's see where you might need this. If I now look at disturbance rejection, okay, what do you notice with disturbance rejection? Well, if it's an output disturbance, again, because there's an integrator, you still get zero offset, and again the simple gain design seems to have done slightly better. If, however, you have an input disturbance, what do you notice now? You notice for an input disturbance, the lag compensator's got a significantly smaller offset than the simple gain design, obviously by a factor of 5, because that's the beta that we used. So the real benefit of the gain recovery for systems with integrators comes when you're rejecting input disturbances. Of course, it will also reduce offset to ramps, but ramps are a fairly rare thing to have to deal with. Right, let's look at the final example now then, and see if we get the same messages. So I've got to clear all my compensators, and then let's import G3. Oops, G3, so import that. And what have we got? We've got a 45-degree phase margin, so I'm going to quickly move this gain plot down and do this one a bit more quickly. So there's my 60 degrees. Let's see what we've got. So we've got a gain of 0.5. It says 0.49, but we'll use 0.5 for simplicity. A crossover frequency of 0.55. Okay, so I can now add my pole and 0. So if you just remember, the crossover frequency was 0.55, so I want a real 0 of minus 0.055 and a real pole of minus 0.011, and then I've got to put my gain back where it was, which was 0.5. So there we go. And what do you notice? Again, we've got our 56 degrees, which is about 5 degrees away from where we started, because we're using beta of 5. You see this classic phase dip to the left. And if I just pull up the responses, again you see this rather slow settling that you get from the lag compensator, because I've introduced this very slow mode. So let's export this compensator. So if I export, and we'll call this one K3 lag, so it doesn't get mixed up with the others. And then we've got to put in the simple gain design, which was 0.5. So there we go, K3 equals 0.5. And now I can look at the Bode diagrams for all of these. So there we go. Where's it put them? There it is. So there's the Bode diagrams, and you see the same message as before. If I make this a bit bigger so it's clear, you can see again the lag compensator. You see this classic phase dip down here, but well to the left of where you're calculating the phase margin. There's the crossover frequency, and you see the gain recovery. You see the red is significantly above the green at low frequencies, so you've got a good gain recovery at lower frequencies, which is why you wanted the lag in the first place. If we look at the step responses, alright, so there's the output responses, and again you notice in this case, because the system included an integrator, the simple gain design seems to have a better response, because it doesn't have this really slow mode. And because you have an integrator, you don't need gain recovery to get zero offset for tracking simple steps. Okay, but what if we look at disturbance rejection again? So here we have output disturbances, and again you see for simple output disturbances the lag compensator doesn't really help. It introduces this slow mode, and it's slower to settle. But if we have input disturbances, again you notice that with a lag compensator you have a much smaller offset in the output. See, this green line is much closer to 0 than the blue line, which is all the way up there. In fact, it will be a factor of beta smaller. So it has helped with the rejection of input disturbances, and also of course will help with rejection of ramps. So a summary: we've shown a number of worked examples of using MATLAB tools to perform a mechanistic lag design. We've reinforced the observations on lag compensators that you can improve the low frequency gain, but the price of this is you've introduced a very slow closed loop pole, and therefore you're only going to use, if, there's a big if here, if the increase in low frequency gain is needed. And if you already have an integrator, it might not be needed. So where a system has an integrator, the benefits of a lag are not so clear cut for tracking performance. Clearly it will help for ramps, but we don't often track ramps. But it does seem to help with the rejection of input disturbances, but if you're only interested in the tracking of the set point or output disturbances, in fact including a lag as well as an integrator can make things worse.